Hi there, this is Dr. Golding, and today we're going to talk about some of the material in 6.6. Yes, 6.6. We're going to skip section 6.5 in the book and move on to 6.6. I won't burden you with an elaborate explanation for why we are skipping 6.5. We're just going to move on to 6.6. Now, in 6.6, you learn a few things which are really very important and helpful for understanding what's going to be coming in chapter 7. First of all, we're going to talk about statement forms and argument forms. Now, in a way, we've already discussed the idea of a statement form, and we've already discussed, in a sense, the idea of argument forms. But we're going to get into a little bit more detail about a concept called substitution instances. One of the things you have to be able to do is tell whether a given statement is a good or valid, correct substitution instance of a certain statement form. You also have to be able to recognize whether a given argument is or is not a case of or a substitution instance of a argument form. And particularly, you're going to have to know that there are certain valid argument forms. All of these things I will try to explain here, and your homework is going to be just to do Roman numeral 1 at the end of 6.6. So that is the homework for unit 6.6. We're in 6.6, do Roman numeral 1. All of the examples in Roman numeral 1. Okay, so let me go back to the idea of a statement form. We'll get to argument form shortly, but basically a statement form is a formula that is made up of simple components that are drawn from the middle of the alphabet, usually P, Q, or R. So for example, if I give you the following statement form, P wedge Q, that is a statement form, P or Q, and there are going to be many, in fact there is an infinite number of substitution instances. Okay, the term I'm using now is substitution instances. There are going to be many substitution instances of this form P wedge Q. For example, I could have A or B. Now, when we use letters from the beginning of the alphabet, generally also capitalized. Notice that A and B here are capitalized. A statement such as A is meant to designate a specific meaningful English statement, whereas a statement form is more like a variable. You know, like you have in math, you have, let's say, something like x plus 2, right? Just to flip over to arithmetic for a second, x plus 2, well, this would be, if you looked at that as an arithmetical form, any number plugged in for x would be correct here. 7 plus 2, 18 plus 2, right? So these symbols, 7 represents a specific number, whereas x is a variable that can take as a substitution instance any number, right? So there's something similar here going on with logic. P wedge Q is a statement form, and it can take as a substitution instance many different possible statements. So for example, what about this? Does this look like a good substitution instance of this form? Suppose I have B dot C or F. This is also a valid substitution instance or a correct substitution instance of P wedge Q, because P can stand for B dot C and Q can stand for F. What if I have something even more complicated, such as F biconditional G wedge Q or Z? Okay, well that's also a valid substitution instance of P wedge Q. Now the rule is that whatever I substitute for P here, if P recurs in the form, now in this case it doesn't, just a P wedge Q, but we're going to get into cases where the same variable occurs several times, or maybe at least once in a formula. So for example, if P is assigned A, then if P recurs again, it's going to have to take the value of A also. I'll give you an example of like that in a minute, but first of all, I want to say, suppose I ask you the following question. I have P wedge Q here. So here's a question. Would this be a good substitution instance of P wedge Q? Now you might be tempted to say, no, this is no good. But that would be wrong. The rule is P can stand for anything and Q can stand for anything. So here, A is standing for P and A is substituting in for Q. So this would be a good substitution instance of P wedge Q. Again, the rule is P can be anything, Q can be anything. The wedge has to stay, of course. So if I said something like A dot B, or I said A dot A, these would be incorrect. Sorry, this is A dot A. These would be incorrect as substitution instances of P wedge Q. Okay, now suppose I have the following. Let me give you a different example. Suppose I have something like P horseshoe P. If that's my statement form, now whatever P is here, it has to be the same here. So A horseshoe A would be a good substitution instance of P horseshoe P. What if I have not B horseshoe not B? Would that be a good substitution instance? The answer is yes, because P can stand for anything. The fact that this has a tilde is not a problem. P is being substituted by not B, and as long as I have the same thing for P whenever it recurs in this argument, in this statement form, so not B horseshoe not B is a good substitution instance of P horseshoe P. If I have something like suppose I have not P wedge parenthesis Q horseshoe P. Okay, here's a statement. Not P wedge parenthesis Q horseshoe P. So a valid or correct substitution instance of this statement form would be any statement where whatever formula I substitute for P has to be the same here. There has to be a tilde hanging out on the left-hand side, negating whatever P is. The major operator has to be a wedge, and then you have to have a parenthesis with a Q horseshoe, whatever P was over here. So for example, a very obvious substitution instance of this would be not A wedge parenthesis C horseshoe. Now do I want to say not A here, or do I want to say A? I want to say A, because what's happening here is that P is being substituted by A, so therefore P has to be A over here. Now this tilde is not internal to P, so whatever P is here P has to be the same here, so this would be a good substitution instance of this statement form. If I had something like B wedge C horseshoe B, would this be a good, this is a good, the top one is good. Would this be a good substitution instance of this statement form? No, because there's got to be a tilde here. The tilde here is part of the form. And so there's no tilde here, so this would be a bad substitution instance, or an incorrect substitution instance of that original statement form. What about something more complicated? Sometimes it's not easy to tell right away whether it's a good substitution instance, but suppose I have this. Look at this. This might seem a little tricky. Tilde, tilde, F, wedge, C dot D, horseshoe, not F. Okay, tilde, tilde, F, wedge, C dot D, horseshoe, not F. So let me get rid of these circles for a second. Is this a good substitution instance of this top form? And the answer is yes, it is a good substitution instance, because look what I'm doing here. I'm letting P stand for not F, and P over here, not F. Beautiful. Okay, so I have not P, not F, wedge is the same. Q is being substituted by C dot D. Remember, Q can stand for any formula. Very long formula, very short formula. So Q is standing for, or C dot D is substituting for the Q. Horseshoe is maintained, not F. Why is it not F? Because P itself is not F. Okay, those are examples of substitution instances of this form. Now let's talk about argument forms. Argument forms. And in particular, we're going to talk about some valid and maybe some invalid argument forms. So an argument form is an argument that's made up of statement forms. So for example, if I have something like P horseshoe Q, therefore Q. This is an argument form. It's a series of statements. I'm designating these as premises. If you like, I'll put numbers here. I got two premises. My conclusion is Q. That's my conclusion. So this is an example of an argument form. It's an argument that's made up of statement forms. Now, we would be using these letters from the middle of the alphabet, generally P, Q, R, S, lowercase letters. And what we're saying is that this doesn't stand for any particular English statement. It can take as a substitution instance any English statement, no matter how complicated. And what we're saying is that if this is a valid argument form, that means any substitution instance of this argument form is going to be a valid argument. Okay? Now, what is a good example of a substitution instance of this form? Well, there's going to be an infinite number of possible substitution instances. The easiest one might be something like, I'm going to let P stand for A. Now that means that wherever P occurs, that it has to be substituted with, or substituted by A. And I can let Q stand for anything. Whatever Q is, it's going to have, in order for it to be a good substitution instance of this argument form, whatever Q is over here, it's going to have to be the same thing down here. So obviously this, okay, this is clearly a correct substitution instance of this argument form. I'm letting P get substituted by A, and I'm letting Q get substituted by B, and I keep everything else the same, that is to say the horseshoe, and so I end up with a substitution instance of this argument form. Now, if this argument form is valid, which it is, you can do a truth table test for this. This is going to be a valid argument form. That means any argument in the universe, which is a correct substitution instance of this argument, is also going to be valid, right? So for example, here's another substitution instance of this argument form. It could be a little more complicated. I could have B dot C, and then I could have B dot C horseshoe not F, and then I have, let's suppose I have not F. So here's a little argument. Is this a good substitution instance of this argument form? I think it is. P is getting substituted by B dot C, right? And then Q is getting substituted by not F, and everything else is the same, meaning the horseshoe over here is right over here, same horseshoe. The fact that there's a tilde here doesn't ruin it, because this whole thing is getting substituted for Q. So we have here a good or a correct, valid substitution instance of this argument form. And so one of the things you have to be able to do is tell whether, actually that's what exercise Roman numeral 1 at the end of 6.6 is really all about, is looking at arguments and trying to tell whether they are correct or incorrect substitutions of valid argument forms. Now, the book, and this is really a good segue into chapter 7, the book gives you several examples of valid argument forms. This is a valid argument form. Let me rewrite it a little smaller, because I'm going to put up on the board here a list of valid argument forms. We have P horseshoe Q, therefore Q. Now, here's something I'd like to say, which is the order of premises does not affect or change whether the argument form is valid or invalid, right? So for example, suppose I give you this. This is a valid argument form. You can test that by the truth table. Suppose I wrote down this, P horseshoe Q, P, therefore Q. Okay? We would say that this is the same argument form. The order of the premises doesn't affect in any way the validity of the argument form. Also, let's suppose I decided to be a little bit different, and I wrote Q horseshoe P, therefore P. I mean, this is also a valid argument form. I flipped the P and the Q order, but that doesn't change anything, right? This is still a valid argument form just as much as P horseshoe Q, Q, right? The point is you have a conditional, and then you have the antecedent of that conditional, and then you infer the consequent. So both of these are examples of the same argument form. Now, there is a name for this argument form, and you have to remember the name of argument forms, or the names of argument forms. This is called modus ponens. I won't try to give you a Latin lecture about why it's called modus ponens. You can read in the book why it's called modus ponens, but we would abbreviate modus ponens by MP. So modus ponens, or MP, is the name of this argument form. You have a conditional, then you have the antecedent of the conditional, and what you infer is the consequent of the conditional. That's modus ponens. Another argument form is what is called disjunctive syllogism. Wow. Disjunctive syllogism. Abbreviated by DS. So disjunctive syllogism goes like this. You have a disjunction, thus the name disjunctive syllogism. Suppose you have P wedge Q, and you have the negation of P, you can infer Q. I think I did a truth table for this last time to show you that this was a valid argument, but again, you have a disjunction, you have the negation of the left hand of this disjunction, and you infer the right hand side of that disjunction. Now, I'm going to say, the book doesn't say this, but I'm going to say this, and this will actually make things a little bit easier for you, is I'm going to say that there are really two versions of disjunctive syllogism. They're not exactly alike, but they're alike in a logical sense of alike. Let me show you what I have in mind. Just a little more room here. Again, the name for this is going to be DS, disjunctive syllogism. Let's suppose I have this. I have P wedge Q, and then I have not Q, and I infer P. Okay, to me, I'm saying this is also disjunctive syllogism. The difference is that you start off, well, this is the same. You start off with a disjunction. In this case, I negated the left-hand side and I inferred the right-hand side. And in this case, I negated the right-hand side and I inferred the left-hand side. So I'm going to say that these are both good examples of the form disjunctive syllogism. And so that means if I come across an argument like, let's say I come across, suppose I come across this argument, A dot B wedge C biconditional F. And now I have not A and B. What can I infer using disjunctive syllogism? What would be a good substitution of disjunctive syllogism? Well, if the conclusion is C biconditional F, we have here disjunctive syllogism. We have a disjunction, we have the negation of the left-hand side, and we infer the right-hand side. Okay? However, this would also be a good instance of disjunctive syllogism. If this is the premise, number one, and now I have not C biconditional F, and I infer A dot B, so this is also a valid or correct substitution instance of the rule disjunctive syllogism. I have a disjunction, I negated the right-hand side, and I inferred the left-hand side. And I don't need the parentheses over here because there's no ambiguity that needs to be addressed by bringing in parentheses. Okay? Now, what would not be a good, just while I'm on this topic, what would not be good is, suppose I did like this. Suppose I had, the same disjunction, and then I had C biconditional F. Can I infer A dot B? Okay, so this would be incorrect. This would not be a substitution instance of disjunctive syllogism because, yeah, I have a disjunction and then I don't have the negation of the right-hand side. I just have the right-hand side itself. So this would not follow, this would not be a valid instance of disjunctive syllogism. In fact, this would be an invalid argument, okay? This would be something like P wedge Q, Q, therefore P. This is a bad argument, okay? Because remember that P wedge Q could be true, even though Q is, P wedge Q could be true if Q is true, and yet P could be false. So this would not be a disjunctive syllogism, and this would be also a fail. It would be an invalid argument. But the point I was making was that there's two versions of disjunctive syllogism. Although the book wants to indicate there's only one version, I'm telling you there's two versions of disjunctive syllogism. If you have a disjunction and then you negate one side, you can infer the other side, not negate it. Okay, let's talk about a few other argument forms. Let's talk about something called MT, or modus tollens. Modus tollens. Modus tollens works like this. You have a horseshoe. I'm going to, just for fun, use R and S to stand for statement forms. R horseshoe S, not S, therefore not R. Okay, you can do a truth table for this argument. You'll see that it comes out valid. If this is true and this is true, it follows that not R has got to be true. This is called modus tollens. The order of the premises doesn't matter, but there's only one version of modus tollens. You have a horseshoe and you have the negation of the consequent. You can infer the negation of the antecedent. So to give you an example of modus tollens, it could be long and complicated, but I won't make it too complicated so it will fit on the board. If I have something like not F biconditional C, and then I have A wedge B horseshoe F biconditional C. What can I infer? Or what would be a good example of modus tollens? Not A? Would that be good? No, that's not good. I need to have the negation of the whole antecedent, not A wedge B. This is an example of modus tollens. Again, a horseshoe, the negation of the consequent, that fits the pattern of R horseshoe S, not S, therefore not R. So that is modus tollens. Let's see here. We have something called the pure hypothetical syllogism. What is the pure hypothetical syllogism? I think we'll just call it hypothetical syllogism and leave out the pure. So hypothetical syllogism abbreviated by HS, hypothetical syllogism is when you have two horseshoes like this, P horseshoe Q, Q horseshoe R, and then you have as a conclusion P horseshoe R. Notice that you have two horseshoes as your premises and a horseshoe as your conclusion. Sometimes logicians, philosophers call Q here the middle term. Q is the middle term. It's the consequent of the first one, and it's also the antecedent of the second premise, and in the conclusion, it drops out, so to speak. So P horseshoe Q Q horseshoe R, therefore P horseshoe R, right? So, and again, now a simple example of this would be, you know, something like A horseshoe B, B horseshoe C, therefore A horseshoe C. It kind of reminds me a little bit of the law of transitivity in arithmetic. It's not the same thing, but it sort of has a similar ring to it, right? If A equals B and B equals C, that means A has to equal C. Well, this is different because this is a horseshoe. This is not an equal sign. But what we're saying is, if A, then B. If B, then C. That means if A, then C has to be the case. If you think about that, it does make logical sense. Also, if you do a truth table for this argument, you will find that it comes out to be valid. So this is a valid argument form. And then what that means is that any argument, no matter how complex it gets, if it follows this same form, will be a valid argument. So, for example, if I have something like A dot B horseshoe C wedge F, and then I have C wedge F horseshoe not X, that's a capital X, okay? So now I could say that A dot B horseshoe not X, that would be a good substitution instance of this form over here. I'm letting A and B stand for the P, C wedge F stands for the Q, and R is getting substituted by not X. Again, the order doesn't matter, right? If I flip the order of these two, it still would count as hypothetical syllogism, right? It's probably not necessary to show you this, but I'm going to do it anyway just to make it very clear. If I have, oh, I forgot my example already. Let me show you a different example where I flip the order. Suppose I have something like F horseshoe G, and I have H horseshoe F. And now I do H horseshoe G. Okay, is this a good substitution instance of this form? Well, I told you the order of the premises doesn't matter, okay? So given that the order of the premises don't matter, the important thing is that you have a middle term, right? You have a conditional H horseshoe F, and then you have another conditional where F horseshoe G, and the conclusion is H horseshoe G. So essentially, this is a good example of hypothetical syllogism. Q is getting replaced by F, P is getting replaced by H, and G is getting replaced by R. So this is a good example of hypothetical syllogism. So far we've talked about disjunctive syllogism, hypothetical syllogism, modus ponens, and modus tollens. There are a couple of examples in the book of bad argument forms or invalid argument forms, which represent fallacies. Remember, a fallacy is a mistaken form of reasoning. So, let's see, maybe we'll put a couple of invalid argument forms up on the board. Okay. Suppose you have something like this. I mean, there are many. There's really an infinite number of argument valid forms and an infinite number of invalid argument forms. But this is kind of a popular one because people sometimes make this mistake, although it's really a pretty bad mistake. Suppose I have, we talked about this actually weeks ago when we were talking about certain kinds of fallacies, not informal fallacies, but formal fallacies. Suppose you have the following: P horseshoe Q, Q, therefore P. Now notice what you have here is, you have a conditional, you have the consequent, and then you're inferring the antecedent. So this is actually a bad or an invalid argument form. Any argument in the universe, any argument in the world which follows this pattern is going to be invalid. And the name for this fallacy is called affirming the consequent, right? Affirming when you affirm the consequent, that doesn't entitle you to infer the antecedent. It's supposed to work the other way around, right? The correct version, modus ponens, that we had on the board a few minutes ago is you have a conditional, and then you have an antecedent, and then you infer the consequent. So here what goes wrong is whoever is making this argument is affirming the consequent and therefore trying to establish the antecedent. If you do a truth table for this, you will see that it comes out invalid. Okay, another invalid form is something called denying the antecedent. Okay, let's take a look at denying the antecedent. Denying the antecedent, you've got P horseshoe Q, not P, therefore not Q. I mean, I give you a very quick substitution instance of this argument. Suppose somebody says like this: if it's raining, then I'll stay home. It's not raining, therefore I'm not staying home. Now that might sound valid, but it actually is invalid, right? If I say, if it's raining, then I'm going to stay home, and let's suppose it doesn't rain. But let's suppose I get sick. Let's suppose there's a TV show on that I want to watch. All I said was, if it's raining, then I'm staying home. But there might be other conditions under which I also stay home. I didn't say, only if it rains will I stay home. I just said, if it rains, I'm staying home. But there could be other conditions which lead me to stay home, for example. Okay, so this is actually an invalid argument form. It's called denying the antecedent. You have a horseshoe. The second premise, again, the order of the premises doesn't really matter, but you have a horseshoe and you have a negation of the antecedent, and you're trying to infer a negation of the consequent. This is an invalid argument form, and any argument in the world which follows this exact pattern, which is a substitution instance of this pattern, is going to be an invalid argument. Now, the book does give you a few other examples of argument forms, which I'm not going to bother going through on the board. There's something called constructive dilemma and something called destructive dilemma. They're a little complicated. I invite you to look at them in the book and see if you can follow the discussion of those argument forms. And you can browse through, but you don't have to worry about. There's a discussion in the book entitled "Refuting Constructive and Destructive Dilemmas." You don't have to worry about that. You should definitely read the chapter, or we're talking about not the chapter, but the section. We're talking about 6.6, and then you should try to do some examples from 6.6 number 1. Okay, just for fun, I'm going to do 1 or 2 examples from the homework just to get you started. So let's try to do this while I'm talking. If you open up your book to 6.6 Roman numeral 1, exercise 6.6 Roman numeral 1, in my book it's on page 371. Okay, that's where the homework is. So let's look at number 1. Number one is N horseshoe C not C, therefore not N. So you're supposed to be able to look at this and determine whether it is a valid argument or not. Is it an example of one of the forms that we talked about? Now, in this case, the answer should be pretty easy. If you remember, we talked about something called MT, or modus tollens. So indeed, this is an example of modus tollens. You have a horseshoe, you have the negation of the consequent, and you infer the negation of the antecedent. So I say, yes, this is an example of modus tollens, and the argument here is valid. Now, there is a little subtlety here which I should talk about. It has to do with what happens when you have double negations. And so the book tells you, a double negation is simply when you have something like a formula that has two negations in front of it. We would call this a double negation. When you have a formula with a double negation, we're going to say that for these purposes you can sort of strip those two negations off in order to determine whether something is or is not a good case of a certain argument form. Okay, so trying to see if there's an example where that comes up. Off the top of my head, I don't see where that comes up. Okay, so I'll tell you what, let me do one more example from this set of exercises, and you'll see as you work through these exercises that there may be a case where you have to get rid of two negations in order to make something fit into a substitution instance. But let's not worry about that right now. Let me just do another example of one of these exercises, and then that will be enough for today's lecture. Let's take a look at oh, I see. Here's, I think, where we have a case. Well, let's suppose we have, let's do number 13. P wedge not S. And then we have S. Therefore, P. Okay. Now, the question is whether this counts as a valid substitution instance of disjunctive syllogism. Now remember, disjunctive syllogism was P wedge Q, not P, therefore Q. We also have the other version, which is P wedge Q, not Q, therefore P. So in looking at this example, it looks like we don't have the negation of not S, but in a sense we do. If we allow ourselves to view S as the same thing as not S, after all, S is equivalent to not S, isn't it? So what the book is telling you is, if you want to look at S as having a double negation in front of it, I mean, this was the original example, but S is really equivalent to not S, and you can prove that by using the truth table. Well, then what we have here is not S, therefore P. So it's going to turn out that this is a good instance of disjunctive syllogism. According to the book, if you allow yourselves to plug in two tildes here, then you have a case of disjunctive syllogism. Now, here's where I would say that this, to me, that's already, I would say that this business of allowing yourselves to add two tildes or take off two tildes is really engaging in another logical step. And so I would be a little wary about saying, okay, yeah, this is an example of disjunctive. It's really not an example of these two forms. If you allow yourselves to throw in two tildes here, then it becomes a good instance of disjunctive syllogism. Anyway, take a look at the exercises at the end of 6.6, these exercises in Roman numeral 1, and you don't have to do Roman numeral 2. That involves translation, and I'd rather you focus on the skill of looking at arguments and telling whether they are good or not good substitution instances of valid argument forms, or whether they're substitution instances of invalid forms. So, yes, just looking at the book one more time, but I think that is enough material to keep you going for the weekend. So if you want to do the exercises and take photos of your work, or if you want to talk to me, email me if you have any questions, please do so. Otherwise, stay healthy, well, and have a great weekend.